So hi everybody, I'm Kyle, and I'm going to talk to you today about neural networks and deep learning. And so the goal of this tutorial is to build up a classifier that can take images of galaxies and tell you if it's a spiral galaxy or something else. We're going to start from the basics and build our way up there. So first thing first, this tutorial what's going on here? Can you see this bar? Zoom, there we go. Oh well. Okay, so this tutorial is meant to be interactive. So I have a notebook that I'd like you all to follow along with if you can. So if you haven't already, please go to this hack.dirac.institute website, and you'll get access to a Jupyter notebook here that has everything installed that we are going to be running. When you go to this the first time, it'll ask you to boot up a different server. You can click any one for this. I've designed the tutorial to use only CPUs, so it'll run on any of the nodes that you can launch there. When you get in here, go into the Astro Hack Week 2020 folder, and then the Machine Learning 2 folder that you can see right here. And then launch, there's this notebook, Astro Hack Week 2020 Neural Networks.ipy notebook. So if you click on that, it'll load up the notebook that I'm going to be going through for this tutorial. So if you haven't already, get that started. I'm going to go through just kind of a few overview things first, so no worries if you're not loaded yet. It'll take a couple minutes, but hopefully you'll catch up by the time we get to actually running things. And so just how I've structured this, so this notebook has a whole bunch of code that I'm going to be running, but there's no fill-in code. You can just run it from top to bottom if you want. And how we're going to do this is at a couple points, we'll pause, and I'll give you an opportunity to play with the models that we've built and try to make your own changes and see how different things affect them. So first of all, let's just start with an overview of what neural networks are and how they're used. Let me just go full screen so you can see this a little bit better. So I want to start off with linear models. So linear models are what we've talked about in a couple of the previous sessions. Basically, you have a function f of x that you write as f of x equals wx plus b, where x is your input, w is the slope, and b is some offset. So in neural network language, we call w a weight and b is a bias. And as you can see, if I choose different values of w or b, I get all sorts of different linear functions. And this plot that I'm showing down here shows you a few different examples of that. So different choices of w and b will give you different linear functions. So this is great if I want to fit a line to my data. But let's say I want to fit something more complicated, like just a simple example would be f of x equals x squared. Well, it doesn't really matter what values of w and b I choose. I'm never going to be able to find appropriate parameters that actually model my function. So this is where neural networks come in. The concept of a neural network fundamentally is it's a function with a lot of different parameters, and with the right choice of parameters, a neural network can actually model any function you want. So there's a couple subtleties to that, but if you have just a single layer neural network that we'll talk about later, and enough neurons, you can actually model any function you want. So how does that work? Well, the key to this is something called an activation function. So in the linear model, oh, I got a comment. Can you post the Jupyter link? Let me just do that. Could somebody else post that for me? Sorry, I can't get out of full screen mode here easily with Zoom. So anyway, the key to a neural network is the activation function here. So for a linear model, you can see we just have a line. Given some value of x, I have some linear output in terms of x. In a neural network, we apply one of these nonlinear activation functions, and here's some examples here that turns this into something more complicated. So for example, with the sigmoid function, you map your value of x to some output between 0 and 1. For very large values of x, you get 1, no matter what the input was. For very small values, you get 0, no matter what the input was. And then there's this range in the middle where you get something in between, where you kind of have the transition from 0 to 1. There's all sorts of different activation functions. They are all suited to different applications, but for simple neural networks like the ones we're going to be starting with here, they can all be used interchangeably. So don't get too hung up on which activation function to use. There's a lot of subtleties there, but for what we're doing right now, any of these will work reasonably well. Okay, so if we combine a linear model with an activation function, we get what we call a neuron. So here's the equation. You take our new model is f of x here, given by some activation function times wx plus v, where wx plus v is just the linear model you had before with two free parameters, w and b. So you should be familiar with that, except now I've stuck it through this nonlinear activation function to get what we're calling a neuron. So here's some examples of what the neuron looks like. This is different parameters, values w and b. You can see as I look at different values of x, I get outputs that go between 0 and 1 because I've used a sigmoid activation function here. And by changing w and b, I can change where the neuron turns on and off, basically. So each of these different neurons is sensitive to a different region of the x parameter space. Okay, so great. I've just made more complicated functions, but it's not necessarily obvious why you'd want to do this. So let's give a quick little example of this. So here I have 4 different neurons. Let's just sum the output of all these neurons together and see what we get. So these 4 neurons here, if I sum their outputs, I get the red line here, which conveniently, because I've chosen the right parameter values, w and b for each of these neurons, happens to give you a pretty good model of the function f of x equals x squared. So for this example, the neurons know nothing about the function x squared. What I've basically done is piece by piece, each neuron you can see is kind of sensitive to a different region of the x space, and it's modeling or giving an approximation to what x squared looks like for that region. And if I add them all up, I've basically made kind of a piecewise reconstruction of the f of x equals x squared function. You can also see here that this function is actually only valid for some regions. So I can model x squared reasonably well between -1 and 1, say, but for values above or below 2 and -2, my neural network's just outputting some constant. And this is something that's kind of important to realize about neural networks, is that they're often only valid on a certain range of inputs. And if you try to go outside that range, you get behavior that might not be what you're expecting. So oftentimes, or when we're actually kind of representing neural networks, you can write them down as functions. So here's the function for this here, my new neural network, where I've added all these different neurons together. I take the single neuron I had before, the activation function times w, or applied to wx plus b, and I sum all these together, potentially with some weights here. So before I just added them all directly, but you can imagine adding some weight that's just scaling it up or down when you're doing the final sum. This is a mathematical representation of what we've done, but we often like to show diagrams because that can be much easier to understand when you're trying to look at more complicated networks. So here is a diagram representing what we've just done. So on the left side is our input. So here we have a single number, which is x. On the right side is our output, which is also here a single number, f of x. And in the middle, we have what we call a hidden layer. So this is all of our neurons that modify the input and spit something out, but we don't actually see them directly because ultimately we just want a function that takes in a number x, spits out a number f, and we don't really care what happens in the middle. So each neuron, for example, A1 here, takes as input x, applies some weight that I've shown on this line here. Inside of this neuron, the activation function happens. So every time you see a blob on one of these diagrams, there's a hidden activation function in the middle. And it spits out a number, and we sum up all of the outputs with these weights w to get our final output f of x. So this is a very simple neural network. We can make this much more complicated very easily.
Can I ask?
Yep.
So each of those A's just represents a single, in our example, sigmoid function?
Yes. So basically each A is a neuron. It's taking as input whatever, all the arrows going into it, taking some linear sum of all of those with the weights given by each of these W's. And then it applies the activation function to the sum of its inputs. So each A is a neuron doing something like these functions seen here. Basically, each one of these lines here would be one of the different A's shown in the diagram. And then to get F, the final output, I sum them all up. So I get something like this. So let's build a more complex network now. So this one just had a single input and a single output, but you can easily have a neural network that has multiple inputs, let's say. So here, I have 3 different inputs. Each of these are just labeled with a different X. And each neuron that I have sees all 3 of those as its inputs. So all I change here is before I was having WX plus B as the input to my neuron. Now for each of the individual X's, I have a different weight W. So here's this written out in equation form. I just have a sum over these WX's rather than just a single one for a single input. But everything else is the same. I sum them up, put them through the activation function, and then so on. Sum everything up to get F. So we can also build more complex, or as people like to refer to them, deep networks by basically taking the output of one layer of neurons and using that as the input to the next layer. So similarly to what we had before, I had all these X's, each of which was used as input to the first neuron here. Now I can just have a second layer of neurons, and each of which sees the output of the first layer of neurons, applies some weight, and gets, and then uses that as its input. So neural networks are basically just combining neurons in more and more complicated ways, and people have come up with all sorts of clever tricks that you can use to make this process more efficient. But there's something important to keep in mind, which is that a single layer of neurons with an input and output can actually model any arbitrary function that you want, no matter how complex, assuming that you have enough neurons. So ultimately, you need an infinite number of neurons to model a more complex function. The point of adding additional layers is basically just to make it easier for us to train our models and be able to use fewer parameters in our final model. But how you design these architectures is a bit of black magic. And mostly it's just trial and error and following up with what people have found effective in the past. And so I'll just
Kyle, oh, sorry. So talking about like needing infinite neurons kind of reminds me of like a Taylor expansion or something. Is it kind of analogous to that? Like if you have infinite sum in your Taylor expansion, you can perfectly model the function?
Yeah, that's a really good point. So basically, how you can think of what the neural network's doing is, in this example here, you see I have 4 neurons, each of which is kind of modeling some small part of the function. And so if I add more and more neurons, each neuron is going to be modeling the function. You can think of it as modeling the function on some small range in X. And if I have enough of them, if I do kind of some piecewise modeling of my function, I can get the pieces small enough that each one will be kind of perfect on the small interval that it has to work on. So the analogy of a Taylor series is really good. It's basically the same thing going on. You keep adding these additional terms, each approximation gets you successively closer. Yeah, so this is a neural network. But right now, all I've showed you is how to write down this model and how to evaluate it. So the next question comes, well, let's say I want to take my neural network and have it actually model some arbitrary function that I have. For example, I have a bunch of images of galaxies. I want to have a function that takes as input an image and spits out, is it a spiral galaxy or is it something else? How do I actually find the values of the parameters for the network that make that happen? And so the key to this is we can train a neural network. So this is something that we do similar to training any other model. basically, we have some loss functions. So this has been discussed in the previous lectures. I have my neural network. I put my inputs through it, put all my images through. Some number gets spit out with whatever the parameters of the neural network were initially set to. I can take that output, and let's say I have a training set where I know what I want the output to be. I can calculate a loss function. For example, I could take the mean squared error difference between the outputs of the neural network and what I wanted the outputs to be. And I can then take a step to try to optimize that loss function by basically saying, what is the derivative of my loss function with regards to each of the parameter values? And I take a step in the direction of each parameter value that minimizes the loss function. So here's kind of the classical example. If your loss function is some nice parabola in terms of your parameters, you can calculate the derivative and move in the direction that optimizes that loss function. There's a bit of a trick with neural networks where often we have thousands or even millions, or I think we're up to billions of parameters for the most complex neural networks. So doing this kind of naive way where you just take your whole data set, calculate the derivative with respect to everything and take a step, just doesn't work computationally. So for neural networks, we use something called stochastic gradient descent, where basically instead of using our whole data set and calculating the exact derivative, we sample a small amount of the data set referred to as a batch at a time, and we calculate the derivative of a loss function with respect to that. So by doing that, we can kind of reduce the computational load, and it actually has some nice properties where it helps avoid local minima because you actually have a bit of randomness in the moves that you're making. So you might ask, how do I actually get the derivative of the loss function with respect to all my parameters? Well, here's an example of that neural network that we had before. Let's say I have this weight here that is the input to this neuron A1, and I want to take my loss function, so that's what comes, the comparison of whatever comes out of my neural network to what I know the output should be for that data set. I can basically just apply the chain rule. So if I have some function, some loss function, then I want to take the derivative with respect to W. I first take the partial derivative of FL with respect to F, the output here, then the partial derivative of F with respect to B with respect to A with respect to W, and finally that gives me this whole derivative. This process is referred to as backpropagation, but it's really just the chain rule that you've learned in all your calculus classes many times. Now, obviously, if you had to do this manually for your neural networks, this would be super annoying because you have a lot of different parameters, a lot of different, I mean, each line here represents some different parameter that you want to optimize. And writing that down by hand would take forever. So thankfully, a lot of very smart people have developed different neural network frameworks that do this for us and make it very easy to build a neural network and train it on some data set. So specifically in this tutorial, we're going to use a package called TensorFlow that was developed by Google to make it easy to build neural networks. And we're going to use the Keras interface to TensorFlow, which is a very beginner-friendly interface that's very powerful. And I think it's actually kind of the most widely used one in industry these days. So this will let us build a neural network quite simply without having to worry about all the math. It'll handle all the math for us under the hood. So let's implement a simple neural network now. So hopefully your notebooks are up by now. So join me down here in the notebook if you can. Here's the neural network that we're going to model. So we're going to have an input x, a single input x, and a single output f of x. And we're going to have two hidden layers of neurons, the A layer here and the B layer here, where each neuron in each layer is connected to all of the neurons or inputs in the layer before it. So all the A's is connected to X, all of the B's are connected to all of the A's, and the output's connected to all of the B's. So this kind of network is called a multi-layer perceptron. That's just the term used to describe it. So how do we implement that in Keras? So this first code block here just imports a bunch of things. So run that. Don't need to worry too much about what it does. TensorFlow likes to output a lot of warnings, especially with the install that's on this hub. So I just shut those all off, but you might be interested in leaving those on normally. So what we're going to do in this example, our first simple example, is to try to model a sinusoid function. So first, let's simulate some noisy measurements of a sinusoid function. So this cell will do that. Basically, in blue is the truth here. So that's the sinusoid function that we want to model. And black is a bunch of noisy observations from our neural network. So each of these observations has an x value that was the input and some measurement, y, that's kind of the value of the sinusoid function with some noise added. We've simulated 100,000 measurements. I've only showed 1,000 in this plot, or 500 in this plot, but there's a lot of data to train our neural network on here. Okay, so let's build our neural network model. So we're going to build this model that I showed up here with 2 hidden layers. There's some parameters at the top of this block here that you can play around with and change if you want. But to start with, we're going to have 50 neurons in each layer. We're going to use a tanh activation function. So just going back up to the top here, the tanh is kind of the squiggly looking thing that goes from -1 for very small numbers to 1 for very big numbers.
And Kyle, do you have any intuition as to why you chose that one?
Well, you should play around with different ones and see what they do. But I'll give you slightly different results. I would say it's not necessarily obvious that one is better for any particular example.
Cool.
At least for what we're doing here. But tanh gives nice results. So. Okay, so how do we build a neural network model in Keras? So we're going to use what's called the sequential interface. This lets you build up your model layer by layer, and basically it'll take every layer and apply it to the output of whatever it had before, which is what we want to do. So first we add an input. Our input has a shape of 1, meaning we're just putting one single number into our neural network. Then we're going to add some hidden layers. So you can change how many you want, but here we have 2. So a hidden layer, how we implement that is with something called a dense layer in Keras. So a dense layer connects each neuron to every element in the layer before it. And these will each have 50 neurons with the tanh activation function. And then finally, we're going to have the output layer. So this is going to be another fully connected dense layer, but instead of having a whole bunch of different neurons, it's going to have a single output, and it's not going to have any activation function applied. So it'll just do a linear sum of everything at the end. So if I run this, the next line does summary. So Keras has this really nice tool where it'll spit out kind of a description of your model. So you can see here, we have our hidden layer that has 50 neurons, our second hidden layer that has 50 more neurons, and our output that has 1 final number output. So this is a really simple model, but I'd like to point out that it already has 2,700 parameters. So that's quite a few. A lot more than you're using in your kind of simple linear models that typically only have 2 or a handful of parameters. And this is the power of deep learning. Because this is such a complex model, it can learn very complex functions. So let's train the model. So how this works, we feed in our x values and our y values, and Keras will fit our model to this data. We're going to use 5 epochs. So an epoch is how often or how many times it runs through the full data set. And so this means each of our input data points will be seen 5 times by the model, and then it'll spit out the final model and whatever parameters it thinks fit best. So let's run this. This will take a few seconds. So you can see we have 100,000 examples in our training set. So just samples from the sinusoid function with some noise. And we're running through. I should skip this, but I'm using a mean squared error loss. So that's calculating the output of my neural network. I calculate the mean squared error between that and the predicted sinusoid value. And you can see the loss function, or the loss output here, shows you the value of that mean squared error as I go through this training set. So it's decreased as the neural network gets trained, which means that we're getting a better and better fit to our data. So let's see how we did. So here I'm plotting the same plot I showed before with the truth in blue and the observations as different black points on this plot. And in orange is the model that the neural network learned. So you can see that for kind of the middle region here, where we have lots of observations, we learned a pretty good representation of the sine function. The mean squared error here was estimated to be 0.06 for our training set. As Stefan pointed out, performance on the training set doesn't necessarily generalize to validation or the test set, and we'll get to that in the next part of this notebook. But you can see that just by eye, it looks like a pretty good fit. What doesn't fit so well is when you get outside of the region where the training data is. So keep in mind, the neural network is being trained on all these observations, but it doesn't know what to do outside here when you get far away from the data. And it kind of just outputs something it outputs something, but that's not necessarily what you wanted it to do. It didn't really learn a sinusoid function. What it learned to do was fit this function piece by piece to try to get some model that represented what the data is. So in general, neural networks are very good at interpolating between where you have a lot of data, and they only really work if you have a large data set to train on. There's tricks to get around this, but that's kind of something that you want to keep in mind, is for a lot of these neural networks, you really need a large training set to be able to get decent results. And neural networks do not do a great job of extrapolating. So I want to have a little exercise here. I want you guys to play around with this a little bit and let me know what you find. So what happens if we change the number of neurons, say? If I go to a few neurons, do I still get a decent representation, or does everything fall apart? And at what point does that happen? You can also try to say, can the neural network learn other functions? So here's sine of x. What if I want to learn like x squared? When does that fall apart? You can try changing the number of layers. You can try making the data very noisy. You can also ask how many observations do I need to constrain the model, so on. So play around with this. Most of these you can just change in this block here. So things like the number of neurons, the activation, the hidden layers, and see what comes out. And please let me know if you have any questions. I'll give you a couple minutes to play with this. I did see one question in the chat. Katerina asked, can Keras also plot our model to get a pretty image like this? So I believe there are packages that people have made to do this for you. I just drew that out myself. So this is not something that Keras made automatically. But I do think that there are some packages that people have come up with to do this that you might want to check out. There's a lot of active research and development in the machine learning community for building things like this. So I guess maybe I'll try one example myself, which is Lauren asked what happens if you change the activation function. So tanh is kind of this nice smooth activation function. What if I try something like relu here? So relu is a function that's 0 if your input's less than 0, and it's just x, so the identity if it's greater than 0. So this is basically just a linear function, except you've chopped off the lower half. So let's see what happens if we try to fit a sine function with a relu, and I got a little lost here. So we'll change that to relu, and Keras has an absurd number of different activation functions implemented, so it'll just know what to do with that. We'll train our model, and you can see the loss is going down, meaning we're getting a better and better fit to our data. So you could do a model comparison if you wanted. You need to have that's a bit beyond the scope of what I'm trying to do here, but you can see we get a decent fit to our data. Now, something that's interesting about the relu function is it's actually, if you model something with the sum of relu functions, you'll get a piecewise linear output. So if you look at this, this is just a bunch of straight lines that are all connected in different ways. And it's used a whole bunch of straight lines to try to approximate the, excuse me, sorry, to try to approximate the sine function. But this is something in general, if you ever use value activation functions, you get a piecewise linear output. And if you zoom in, you'll see the individual pieces if you look closely. Sorry. So play with this a bit more. Let me know if you have any questions. But I'd also like to get on to the second half of this tutorial, where we're going to actually move into deep learning, where to try to classify galaxies. So there's a couple more things we need to know if you want to do typical deep learning. You can keep just stacking more layers like we were doing before here by just, going back to this. Just keep adding more layers of neurons like we saw here. But at some point, you don't really get that much of an additional benefit. Because as I said before, a single hidden layer with an infinite number of neurons can actually represent any function. So the key is if you're adding more layers, you want each layer to kind of learn different features in the data. And this is something where something called a convolutional neural network comes into play that lets us build much more complex models with many fewer parameters than just a simple application of more fully connected layers. So a convolutional neural network, what it does is it applies the same function to every point in your input image. So it takes every point in your input image and applies some kernel, which is some function that looks at that pixel and the pixels around it, applies some function to that and outputs a number. So it'll take your input image, say this thing on the left, apply some function to all the pixels within this box, and store the output in this pixel in the output image here. So it takes an image as an input and outputs an image as an output, where the output has kind of, for each pixel, it's looked at some range around that original pixel. So a typical kernel size is something like 3 by 3. So it means for each pixel in the image, you look at that pixel and the pixels one step around it in any direction, apply some function to those, and spit out an output. Now you use the same parameters for each of these kernels in the input image. And what that means is that if I take the image and shift it, let's say, by a few pixels over, I'll actually get the same output shifted by a few pixels from my convolutional layer. So these are very powerful tools. And basically, they decrease the number of parameters you need a lot compared to connecting all of the input pixels to all of the output pixels, which doesn't necessarily add that much for you because you're mostly interested in trying to find local features originally. So for a convolutional net, we kind of build it up. The first convolutional layer will look at just things in the vicinity of your pixel, and we can combine this with a technique called pooling to take our image and condense it, make it smaller at each step, and start to learn features that are on larger and larger scales in the image. So how pooling works, it's pretty simple. Here, this is a technique called max pooling. If I have an input image that's 4 by 4, I divide it into 2 by 2 grids, say, and in each 2 by 2 box, I just take the maximum value of all of the pixels in that box. So for example, in this box of 4 pixels, this pixel had a value of 5, so I take, which was the biggest, so I spit out 5 in the output here. This one had a value of 7, so I spit out the value 7 here. So pooling like this lets me take a large image and kind of collapse it to get a smaller one. So if I repeatedly apply convolutional layers in pooling, what I get is what we call a deep convolutional network. So here's an example of this. This is one called VGG16. And back in 2014, this was the state-of-the-art network that was able to classify images of 1,000 different kinds of things. So cats and dogs and bicycles and things like that. Could tell you what was in the image out of 1,000 different things with about 90% accuracy, which is pretty impressive. And all it did was take your input, which is, here it was a 224 by 224 pixel image with 3 color channels, so red, green, and blue. Stick that into some convolutional layers, and then you apply max pooling to decrease the size of your image. Keep doing that over and over and over. And eventually you stick this through what we call a fully connected layer at the end, which is just what we had before. You take all the outputs of this final max pooling and put them into individual neurons. And at the end, it just spits out 1,000 numbers, which you can interpret as each one of those 1,000 numbers corresponds to a different class, like dog or cat or bicycle or person. And it uses that to predict what is in the image. So let's adapt this network to classifying galaxies. And it's okay if you got a little lost on this. You can understand kind of the fundamentals of this layer later. Now we're just going to build the network and play with it. So that should be fun. So for classifying galaxies, the goal here is we're going to take a picture of a galaxy and spit out if that is a spiral galaxy or something else. So there's this data set here from Nair and Abram in 2010, where they manually labeled a few thousand images of galaxies. And I pulled some postage stamps from SDSS so we can see what the galaxies look like in a few different bands. And I'll say this tutorial is inspired by a similar example in Astro that I believe Brigitte, who's one of the organizers for Astro Hack Week, developed. So thanks to her for the inspiration for this and for the data sets. So here's the data set you can load in. There's all sorts of different things, but all we're going to care about is if it's a spiral or not. But feel free to go play with things like you could try predicting the age or something more complicated. Let's load the images. So these are all stored in my home directory on the Astro Hack Week server. Hopefully you should be able to access those. Let me know if you have any problems with that. And let's plot a few images to see what this looks like. So here you can see some images of our galaxies, and on the top is the label from this paper that the authors came up with. So we've got ellipticals, we've got spirals, there's some lenticular galaxies, and then each time you run this, it'll actually give you a different set of galaxies to look at. So there's some peculiar ones too that have more complicated things going on. So our goal is going to be to predict, is it a spiral or is it something else? We're going to keep it simple for now. So they have the T-type in here. We can convert that into what I call label here, which is just whether or not the galaxy is a spiral. Here, because we want to see what the performance of our final classifier is, we're going to split our sample into training and test subsets. So here I've just picked every other. You can use, there's all sorts of things in sklearn that you can use to do more complicated splits, but this just keeps things predictable for now. So half of our images are going into a train set that we're going to train our model on, and half of them are going into a test set that we can use to evaluate our performance later. And then let's build our CNN model. So we're going to build something inspired by the VGG16 architecture that you see here, where we basically just keep alternating these convolutional layers and pooling layers, and then finally we'll condense everything down, and in our model we're just going to have one output. So you can see that here we start with an input that is a 100 by 100 by 3 image. We just have 3 different bands, but you could extend that to more if you wanted for astronomy. And we add our convolutional layers. So how this works is 3 here is the kernel size. So that's how many pixels you're looking at around your pixel. And then we output a certain number of channels. So an image with 3 channels is what you're typically seeing with RG and B channels. But for neural networks, you can have as many as you want. So we actually increase the number of channels as we go through to try to capture all that information. Finally, we stick everything through a dense layer and add another dense layer at the end with a sigmoid activation that'll spit out a number between 0 and 1. So this is our basic neural network. To train this, ultimately what we want is to predict if we have a spiral galaxy or something else. And we're actually going to predict something akin to a probability, where it outputs 1 if it thinks it's a spiral galaxy, 0 if it thinks it's not a spiral galaxy, and some number in between if the network's not so sure about it. I'm not going to get into the details here, but the loss function of binary cross entropy basically rewards the neural network for outputting something akin to a probability. Probability I use as a bit loosely here because probabilities output by neural networks are not real probabilities, but they kind of behave like it. So be aware of that. So let's compile our model. You can see Keras outputs this nice description of our model here. This thing has 43,000 parameters. So that's a lot of free parameters to tune to model our data. But thankfully, we can fit that to our big training set and hopefully get some reasonable constraints. So,
Kyle, can you say more about the channels again? I think I understood in the convolution part, the number of pixels, but I got a little confused about the channels.
Sure, sorry, yeah. So a channel is kind of like, for a normal image that we see, the human eye can see red, green, and blue. So those are different channels in the neural network speak. So a typical image that humans like to look at has 3 channels, but you could also make like a 1-channel image that would just be a black and white image. Or in astronomy, you can imagine oftentimes we have images of a galaxy in, say, 6 different bands. So I have 6 different images, each of which is looking at kind of some different aspect. But each of those images I know is aligned in that the pixels that are at the same location are looking at the same part of the galaxy. So if I add more channels, it's basically just having more images of that same object. You can think of it with different filters or different bands in astronomy applied. So the neural network here will, at the end of the day, it'll make kind of a 6x6 image, but there's 32 different bands that it's looking through. So each of those 6x6 images, the pixels line up with each other, but it'll be capturing some sort of different feature. So for example, you can imagine the neural network would try to identify, are there spiral arms? So one channel might be, is there a spiral arm in this pixel? That could be something that it's trying to look at. Another channel could be like, is there a bar in this pixel? Or something like that. So interpreting neural networks is something that's very complicated and a lot of work is going into that. But basically, each of these channels, you can imagine trying to learn some sort of different structure of the image, ultimately. Does that kind of make sense?
Yeah, I think so. I think I got confused because I thought it required, because I was thinking in RGB, I was like, oh, then you need like 8 filtered images of that galaxy. But it's not that it's inputting that many channels. It's that it's trying to like learn that many channels about the image, kind of.
Yeah, exactly. So we're just used to looking at 3-channel images, but an image can have as many or as few channels as you want. So I see a question on the Discord. What if, say, you're dealing with images of galaxies and their spectra? Can you make the spectrum an additional channel? So that's a really good question. For this convolutional style network, that's a bit tricky because basically this is designed to take an image and spit it down to something else. But you can actually add kind of alternate paths to your neural network. So at this stage here where you have this fully connected layer, you can imagine actually taking the spectrum and just using it as a second input to that layer. You can do all sorts of complicated things that you want. Typically, though, it wouldn't be an additional channel unless you actually had kind of spectrophotometry where you had an image of the galaxy at each wavelength, which is something that happens for some experiments. So let's train our network. So we're going to train our network now. So first of all I've done at this point is written a function that takes as input something that's a 100 by 100 image and outputs one number. I can train this to approximate any function that I want. So you can take this and try all sorts of different things if you'd like. So here we'll train it to predict if the galaxy is a spiral or not. This will run. Processing images is a bit slower because there's a lot of computation happening, but this will run in about a minute or so to train on a CPU. As an aside, you can also, doesn't look like it's doing so great. Fingers crossed. This is a random demo where it picks different images every time. Oh, okay. So I'm looking at the accuracy here. This is how accurate it is on the training set. It was a little slow at first, but it's getting better now. So we're getting near 80% accuracy after 3 epochs. As an aside, we're training on a CPU right now. A lot of the big advances of neural networks happen when people figured out how to do this on GPUs, and packages like TensorFlow and Keras and PyTorch and all that are basically designed to do all this on a GPU. And you'll see a speed up of a factor of 100 or something like that typically. So if you're actually serious about this, you can spawn up one of the GPU notebooks and play around with that. Okay, so we trained a model. Let's use it to predict whether each of the images in our test set is a spiral galaxy or something else. So let's predict this. We get, for each image in our test set, a probability. And I use probability in quotes here because this isn't a real probability, but it's something that kind of looks like it, of each image being a spiral or something else. So here's just a histogram of the counts. So you can see for a good number of images, it outputs something close to 1, meaning it's very confident that it's a spiral. For another group of images, it outputs something close to 0, meaning it's very confident it's not a spiral. And there's a bunch of images somewhere in the middle. So let's just look at a random set of predictions. So on the top here is the label that came from the original data set. And on the bottom is the output of our neural network. And this is for images that the network hasn't seen at all. So it's trying to figure these out for the first time. So you can see for these two ellipticals, it said, nope, that's not a spiral. I'm very confident that it's not. But then the neural network also makes mistakes sometimes. So this galaxy, it says there's only a 6% chance that that's a spiral when it was labeled in the data set as a spiral. So we didn't do very well for the spirals in this one. It got a lot of them wrong. But this is a pretty simple network. So this is what we're starting with. Here it did better. So it got that one, 99%, or 0.99 probability of spiral. Here's another one that got well. Did pretty well for that set. And we can look at some bad predictions too, let's say. So here are some predictions that I just looked at ones where we predicted or made a prediction that was in the wrong direction from what the output should be. So here's a spiral that it got just completely wrong. I don't know what happened there. I don't think we got a very good model with this training iteration, but try it again. There's a lot of, this is all random for this data set that I made. So you'll get different results every time you run it. But yeah, so now we've built a model that can take an image and spit out a number that's whether it's a spiral galaxy or something else. So I'm looking at the chat. I got a whole bunch of different messages. Let me just read through this. It looks like people have been going through and answering questions as I go. So yeah, there's a bunch of different questions about CNNs. So CNNs, I think, personally, when I like to use them are when you have translational invariance in your input. So what a CNN is good at is it's basically applying the same function to each pixel individually. And what that means is that if you shift the whole input by like a few pixels over, it will give you the same output of the CNN, just it'll give you an image shifted by a few pixels over. So that's very useful when that's what your data looks like. And in this case, that's kind of what's going on. We have these images of galaxies. We've aligned them in the center, so it's not quite translationally invariant to start with. But if you want to pick up like the small features out here, you don't really care where in the image the spiral arm is. It's a spiral arm. And the convolutional neural network is very good at learning features like that that could be anywhere in the image. There's something about the channel information, replacing them with the numerical quantities in each pixel. So yeah, neural networks just operate on numbers. So you need to take your image and represent it as a bunch of numbers. Here we're just plotting it in color so humans can see it, but what these images actually are is each one is 100 by 100 pixels, and it's got a red, green, and blue channel, and each of those red, green, and blue channels actually has an integer number between 0 and 255. Neural networks like it when you take the input and normalize it to roughly between 0 and 1, so I've divided that. but basically each pixel is just a number between 0 and 255 that you can look at if you look at the raw data. And in general, you can take any astronomy data. I mean, most of it is just counts on a CCD anyway, so you can take that and turn it into a number to stick into the neural network. So I've got a few more minutes. So I'd like you to play with this neural network. I'll show you a couple of quick little things before we get to the end of this notebook. One thing we can do is plot a confusion matrix. So I think Stefan briefly discussed this. Confusion matrix, you'll see these in most most machine learning papers actually. What it is you show the true label on the left and the predicted label on the bottom. And I've just chosen a threshold of everything above a probability of 0.5 is a spiral galaxy. Everything below that probability is not a spiral. And you can see for the true spiral galaxies, I predicted 432 of them in my test set were spirals, and 113 of them I got wrong. So roughly I had 80% accuracy for that threshold. And in general, you can extend this to have more classes. So you can have, maybe you want to be actually predicting it. Is it a spiral? Is it lenticular? Is it elliptical? And that would just add more rows and columns to this plot. So this is something you'll see pretty often in different machine learning papers. Another thing is something called a ROC curve. So this was for a specific probability threshold of 0.5. But if I can tweak that threshold up or down to get more or less, basically as I tweak that up or down, I let more or less of the kind of questionable objects into my sample. And so by changing the threshold that you're using, you alter the true positive rate, meaning what fraction of all of the images that are actually of the class that we want, we identify correctly as being of that class. And the false positive rate, meaning what fraction of the objects that were of the other class I confuse and let into my sample and say that they're part of the class that I was looking for. So in this case, with a probability of 0.5, we were seeing that we got about 80% true positive rate, meaning that 80% of the spirals we called a spiral. And we have about a 10% false positive rate, which you can see here. We had about 47 of the 408 non-spirals we called spiral galaxies. So there's a metric we can use called the AUC, which is the area under this curve of the true positive rate versus the false positive rate. That's 1 for a perfect classifier and 0.5 for a horrible one that just outputs random guesses. That would be a line here where the false positive rate is the true positive rate. So here we got an AUC of 0.92, which is generally a reasonable number. I mean, what's acceptable or not depends on your application. So there's a lot of discussion in the different chats, but it looks like other people are helping out and answering questions for me. So I guess feel free to ask questions on voice if you have something you want to ask. But if not, I'm going to assume that all these volunteers are doing a great job, and I'll jump into the chat later. So we're pretty much out of time here. I'll say there's an exercise here that I think you should go ahead and play with if you're interested. You can do all sorts of things to change your classifier. So you can change the architecture, you can train for longer, use better input data, add additional layers, change the loss function. There's all sorts of tweaks you can do. A lot of neural networks is kind of just trial and error. There aren't really necessarily theoretical reasons to prefer one model over another in a lot of cases. And people just experiment and figure out what works best, especially with things like changing how many different layers you have, the sizes of those layers, the number of channels. These are all hyperparameters that you can tune. And in fact, people are actually using machine learning to try to build neural networks. So there's this meta neural networkness going on right now, where you have a neural network that builds its own neural network. It's an active area of research. But yeah, so play around with it, and as a fun challenge, whoever can build the best classifier wins. I don't have a prize. Wins the title of Ultimate Galaxy Classifier, let's say. So maybe let everybody know in the chat if you come up with some good models. I've added some additional topics here that you can read through if you want. These are different things that you can use to improve your network. I'll say just briefly in my last minute here, one thing that's very important to keep in mind is representativeness. So you need to have, for a neural network, you really want to have a training set that is representative of your test set. And if that's not the case, then you're not going to get good results. So for example, here we use a training set that was primarily restricted to low redshift galaxies. So it likely won't generalize very well to high redshift galaxies. And if you tried to take this model and apply it to some high redshift galaxies, you'd probably have a very biased analysis. This is especially important to keep in mind, as Stefan was pointing out yesterday, when you're trying to use neural networks for tasks where people are involved. If you train a neural network on some data set that omits a group of people, say, from it, you could get very biased predictions for that group of people when you try to actually use the model in real life. And a lot of neural network models have, a lot of training sets that people typically use have significant biases in them, trained, for example, on data collected in the US, but then are being applied in other countries or things like that, that could potentially impact people in the real world. So be careful and think about what you're doing when you're using these models, especially if people are involved.